Hello everyone, I am Pushpita Chanda. I am a PhD student at IIT Delhi. I am the tutor for this course, Applied Optics. So I hope I am audible. Mm. And one thing that after 1 hour maybe uh, the call gets ended. So for that I have created another email link, Gmail link. So let me share that with you. So please join via that link, and I'll also post that link in the Q&A section of the courses. So let's start. Um, So before starting the content of week 2, first I want to discuss quickly the question of week 1 of the previous year, not this year, but the previous year, and they are very easy. So I think we will be able to finish very quickly. Uh, so the first question was that visible light is, okay, let me use visible light is, and the options are mechanical wave, B electromagnetic wave, C longitudinal wave, and D none of this or all of this. So we know that visible light is an electromagnetic wave. That light can be described as like the optics can be described as the ray optics or geometrical optics and the wave optics, and that wave is basically electromagnetic wave. So the option B is the correct answer. And sound wave is more of a like longitudinal transverse wave. No, the sound wave is a longitudinal wave. Uh, question 2. Question 2 is a wave moves through us through the space, transporting A, only energy, B, only momentum, C, both energy and momentum, D, medium. So we know that when a waves maybe like especially here when a wave we call we will like think of an optical wave which is an electromagnetic wave, and when an electromagnetic wave moves through the space, so it both transport energy and momentum. So basically the question C is the answer. And the other way the question can be asked that when a wave moves through the space, which of the conservation like rule follows: energy conservation rule, momentum conservation rule, or both energy and momentum conservation. So both energy and momentum conservation rule follows when a wave moves through the space transporting. uh, so basically this question can be asked in two ways. The third question, question number 3, is wave that can these are very like straightforward theory based question. Propagate even in the absence of a medium is mechanical wave, longitudinal wave. C is electromagnetic wave. D is none of this. So we know the sound wave is the longitudinal wave, and for sound wave we need a medium. Without the medium the wave cannot propagate. Same for the mechanical wave. The mechanical wave also propagate via medium. Uh, only the electromagnetic wave or the light, uh, I should not say the electromagnetic wave or the light. Basically when we say the light, we assume that light only in the optical region which we can see the color and all those things, but the electromagnetic wave is the total spectrum. So the electromagnetic wave can propagate even in the absence of the medium. So that's how the light from the sun came to earth, and most of the space between the earth and uh, sun is it's not even, like you can say it's vacuum, or in, or the absence of medium. Actually the vacuum is also not the absence of medium. So they are technicalities. So basically always remember that electromagnetic wave can propagate even in the absence of the medium. It doesn't require a medium. Whether in the sound wave, so in how does a sound wave propagate? So when the sound wave propagate, it like I should not draw it like, but when sound wave propagate, so the medium get compressed, then it rarefied and so on. So that's how, the and the movement of the medium is in the longitudinal direction of the wave. So that's how it propagate in the medium. Whereas most of the electromagnetic wave, we can say that it's a transverse wave, because we know that for electromagnetic wave, if this is the propagation direction of propagation of electric field, and this is the direction of propagation of magnetic field, then wave will propagate in this direction, or we'll say the wave vector k will propagate in the transverse direction of this E and M. But this is not the case for the sound. So the next question is, question 4. So whatever I was explaining in the last question, that sound propagating in the air, the sound need a medium. So how does basically sound propagate? So the sound is created when, or I should say, the sound is originated sound originates from a vibrating object. So basically when we talk, it's basically a like vocal cord. When we sing, it's basically a musical instrument. And in different musical instrument, different medium, different thing vibrates. Um, so in a drum, only the membrane vibrates. In like flute, the air actually make the sound, and in the guitar string vibrates. So the sounds basically originates from a vibrating object, and this vibrating object create areas of high pressure and low pressure. In common word for high pressure, think we call it as a compression, and for low pressure area, rarefication. In the medium. So this pressure variation cause the particles to oscillate back and forth. So basically we can draw it like this. Then here so here it's like rarefication, here it's compression, here it's again rarefication. We can like take a similar picture of like this. So that how then one particle got displaced and it gets collided with another particle, and the oscillation got passed through the other particle, and that's how the disturbance got transferred, and it like move forwards. So it's like a longitudinal sound propagating in the air will be the longitudinal wave, because the particle movement is in the direction of the wave. So that's the reason. Sound is also a mechanical wave. Always remember that here, wave that can propagate even in the absence of the medium is mechanical wave, longitudinal electromagnetic wave. So mechanical wave sounds, which is a mechanical wave, is also a longitudinal wave. Uh, um, um, uh, it's not necessary that all the mechanical wave is longitudinal wave, or all the longitudinal wave is mechanical wave, but sound is the example of the both. So the question 5 is the relation connects frequency and angular frequency. So this is f on nu and this is omega. So there are option, that is f is equal to 2 pi omega b, omega is equal to 2 pi f, c is omega is equal to 2 pi by f, and d is none of this. We know that omega is equal to 2 pi f, so this is the correct answer. And last day I have also discussed, let me show the file. Okay, I have discussed all the equation regarding this. There is a problem opening the file. No, why this is happening? Yes. So see, I have discussed these equations. Omega is equal to 2 pi f or 2 pi nu, and v velocity is lambda into nu frequency, and wavelength time period we can say that that is 1 by frequency, and k, the wave vector, is 2 pi by lambda, and we can denote the light wave as a sine kx minus omega t, kx minus omega t s phase. We can also denote it as a cos kx omega t. It doesn't need to be the sine always. Basically, it needs to be a like periodic harmonic wave. The question number 6 is, in a wave, the speed of propagation of constant phase is called omega, or angular frequency. B is propagation constant, or k. C is called groove velocity, phase velocity, sorry. And D is amplitude of the wave. So as I have discussed in the last tutorial, that this is the phase, and the phase move with del x by del t, which is omega k, which is called phase velocity. The velocity at which the phase moves is the speed of the propagation of constant phase. So this is the right answer. Question 7 is the displacement associated with a wave is given by y xt is equal to 0.5 cos 0.3x minus 2t, where length time are in micrometer and in second respectively. The amplitude of the wave will be question number option A 0.3 micrometer, option B 2 micrometer, option C 31.4 micrometer, option D is 0.5 micrometer. So the wave has given by 0.5 cos 0.3x minus 2t. So we'll compare it with our standard form of wave, that is a cos kx minus omega t. We are considering a cos kx minus omega t as here it is cos. So we know the a is amplitude, basically k is here 0.3, omega is 2. Here it is also written down. The length is in micrometer and the time is in second. So this is in micrometer and this is in second. So the amplitude is basically, here we can see that it's 0.5. Now, so the answer would be D 0.5 micrometer. So basically say that this thing is called amplitude. Question 8. 8 is basically a double concave lens is made up of a material whose refractive index is 1.34 and the lens is kept in a liquid of refractive index 1.47. It will behave as a converging lens, B diverging lens, C plain glass surface, D none of this. So basically a so it is double concave lens. Basically, the normally double concave lens behave as a diverging lens, but when it is in air, so the air refractive index is 1. But if double concave lens is kept in a surrounding whose refractive index is more than the double concave lens, it will act as opposite, that is converging lens. That is similar for convex lens also. Convex lens is always a converging lens, but if we kept in a medium whose refractive index is more than the material, it will act as a diverging lens. Because of the formula, we know f is equal to n minus 1, 1 by r1 minus 1 by r2. So here n is basically ratio of n2 by n1. So n is equal to basically n2 by n1, and the ratio here is less than 1. So this will give a minus, and this will give a minus, minus, minus positive, and that will behave as a converging lens. It was question number 8, and now question number 9. Question number 9 is an object is placed 100 centimeter far from the single spherical concave surface of radius of curvature 40 centimeter. The image will be formed at number A 16.66 centimeter, then B 66.66 centimeter, option C 28.5 centimeter, option D 25.00 centimeter. So the object is at 100 centimeter from a single spherical concave lens. So here is the answer. That that is n2v minus n1u is equal to n2 minus n1 by r. So here we know u is equal to minus 100, r is equal to minus 40, because we are dealing with concave surface, not convex surface, and if we put this value, we will get phi is equal to minus 25 centimeter. Okay, this every option has minus option with that. So if we put this value here, n1 is 1 and n2, which is the class, we will say that class refractive index is 1.5, or no, the class refractive index is not 1.5, or 5, it is 1.33. Okay, that is 1.5 actually glass refractive index varies a lot. It is between 1.4 to 1.7. You can say that it is 1.5, and water refractive index is 1.33. Okay, so if you put these values here, so you will get V is minus 25. Question number 10 is equation of a harmonic wave propagating along x-axis at t is equal to 0 with amplitude 5 meter and wavelength 50 meter is a y is equal to 5 sine 2 pi x by 50, b is equal to y 10 sine pi x by 50, c is equal to y 5 sine 2 pi x by 25, d is equal to y 10 sine 2 pi x by 50. So we need to know that at t is equal to 0, so psi xt is basically a sine kx minus omega t. At t is equal to 0, it would be a sine kx. So k is equal to 2 pi by lambda. So here it was said that amplitude is 5 meters, so a is 5 and lambda is 50. So the waveform would be 5 sine 2 pi by x by 50. So that is this is the right answer. So these are the question from the previous year week 1. This year's week 1 questions, like basic, I have discussed last week while discussing the theory, and I have like discussed some questions as well. So that's why I took the very long time to explain the theory, that how the lens, this is the formula, lens focal length, lens maker formula, then from that lens maker formula we get lens formula. This is Lagrange's law, and some question, find the angle of refraction, how can you get that, and so if we are given a wavefront and the phase velocity and k is given, how can you find the angular frequency? So this kind of questions, that when do you use Newton's formula, that like question 4 here, which I have discussed in the last week. So I have discussed some basic week 1 subject questions in the last week, and now I have discussed the previous year week 1 quiz question. So I think that should be enough to solve for this year's week 1 questions. Anyway, I'll like solve it in subsequent classes if many people says that, or even anyone says that there is a problem with the question. So concluding that, now I go into the content of this week, that is the matrix method. Basically, in paraxial optics. So first thing, we need to know what is paraxial optics. So basically, by saying paraxial optics, we only consider rays which are very close to the lens axis or the system of lens axis. And makes very small angle with that axis. So one, they need to be very close, and they need to make very small angle. So why we need to convey both of the thing, that it should be very close, and also the make angle, small angle with the lens. So basically, see, this is the lens axis. We can you can say that if we only include the criteria of the angle, then this ray will also be considered in the paraxial optics, but it will cause aberration. So that's why in paraxial optics, the first and foremost assumption is that the ray is very close to the lens. So that is the criteria of the paraxial optics, and in this matrix method, we need only two parameters. It is the distance of a point from the horizontal line of, basically the horizontal line is the x length axis, and b, that is denoted by x, and another thing is called lambda, that is optical direction cosine, which is denoted by basically n cos alpha or n cos psi sin alpha. So what is the difference between psi and alpha? Alpha is the angle from the horizontal axis, not horizon, and psi is the angle with vertical axis. So basically, if the ray is going like this is alpha, this is psi, and lambda is equal to either n cos psi or n sin alpha. So we will take the n sin alpha approach, and you know that when alpha is so small, sin alpha is equal to tan alpha is equal to sin alpha is equal to alpha, and also tan alpha is equal to alpha, and cos alpha become 1. So that's why lambda is equal to n sin alpha became n alpha. So we have two parameters, lambda and x. So depending on these two, and now you know every optical thing can be defined as a combination of translation matrix and refraction matrix. For the purpose covered in this course. Otherwise, there is a matrix for different thing also, like give me a minute. There is a matrix for reflection also. The reflection matrix from the plane interface, then mirror matrix. There are many kind of matrix there. So here we will be, so for the sake of mention, that the spherical mirror matrix is like this. So they are some variation of translation and reflection matrix may be away. So this is like spherical mirror matrix, and there is thin lens matrix that you have. They are the combination of this translation and reflection matrix, and the refraction matrix from the plane surface, refraction matrix from spherical interface, a different kind of thing. So basically now we'll go into the very basic of translation matrix and refraction matrix. So for translation matrix, basically 1 0 d by n1 by 1 lambda 1 x1. When see there is a 2 point A and B, and they are making all this is translation without any refraction, and when translating they will make the same angle alpha and alpha. So you can see that lambda 2 is equal to lambda 1, and they are in the same medium. So basically this is the relation between two lambdas, but this is x and x1, this is x2. So x2 is equal to, basically if it is this distance is d, this is tan alpha, so x2 is x1 plus tan alpha. From that equation this translation matrix came, and it denoted by t, and determinant of t is always 1. And from the refraction rule, that's Snell's law and all, we get a refraction matrix also, and that is basically lambda 2 x2 equal to 1 minus p 0 1 lambda 1 x1. And what is p? P is equal to basically n2 minus n1 by r. So if this is n2, this is n1, and the curvature is r, then p is n2 minus n1 by r, that 1 minus p, and the refraction matrix is denoted by r, and here also the determinant of r is equal to always 1. So now the next thing is that how the total matrix for the refractive surface. So form an image by a refractive surface. So basically how we define that this is the ray, okay, O, and it has an image at I. So you can say that is lambda 1 x1 and this is lambda 2 x2. But between this lambda 1 x1 and we need to understand what is happening from this point to this point here, say lambda 1 dash x1 dash. This is pure translation, and from there is a point here exact after the refraction, lambda 1 dash dash and x1 dash dash. So between this only refraction matrix will work, and that lambda 1 dash dash and x1 dash dash to that I point there is another translation. And you need to remember very carefully that the order of a matrix, it is very, very important. So lambda 2 x2 is basically, we need to start from here. We need lambda 2 x2, right? We know where is the object. we need to find the image. So that's our task basically. So we start from here. So lambda 2 x2, the direct correlation what it seems at the first glance with lambda 2 x2, we have correlation lambda 1 dash dash x1 dash dash, and this is translation. So we will write a translation matrix, and that is 1 1 0, and obviously we are assuming this distance is u and this distance is v. So the distance is v and divided by n. So for the sake of simplicity or the general purpose, this is the n and this is n2. Now we don't know what is lambda 1 dash dash and x1 dash dash. Now we need to find that. So lambda 1 dash dash and x1 dash dash is directly related to lambda 1 dash x1 dash, and their refraction happening. So we need to write a refraction matrix. Again, we don't know what is lambda 1 dash dash and x1 dash dash. So basically for that we need a translation matrix, and that matrix is minus u by n1 here and this lambda 1 x1. Now we need to establish the relation between lambda 2 x2 and lambda 1 x1. We need to start replacing this, that at the place of lambda 1 dash x1 dash we need to replace the total thing. At the place of lambda 1 dash dash and x1 dash dash we need to replace the whole thing. So the matrix after all this will be v by n2 1, then 1 minus p0 1, then 1 0 minus u n1 1. The order is very important in the matrix. We know from the mathematics knowledge that order in the matrix multiplication is very important. So we are using matrix multiplication here. So here also in the matrix method in paraxial rays, the matrix method in paraxial optics, the order is very important. This is the order. Now if we multiply all those things, then we get something like this, and here v by n2 1 plus p u by n1 minus u n1, and there is 1 minus vp by n2 lambda 1 x1. Now there are different the approximation that for axial object x1 is equal to 0. For axial object means the object which lies on the lens axis. So obviously x1 is equal to 0, x2 is equal to 0. So when x1 is equal to 0 and x2 is equal to 0, basically when we are writing the matrix like this, lambda 2 x2 is equal to this thing. So basically we are saying that x2 is, let this value is a, so a lambda 1 plus 1 minus v p by n2 x2. So then when x1 is equal to 0, x2 is equal to 0, that a needs to be 0. So when we put that thing v by n2, a is basically that whole thing. Minus u by n1 is equal to 0. We get some relation. From that, we get n2 by v. Not from that, we already know n2 by v minus n2 by n. From this, p, we get wait a minute, something is missing here. From this relation only we get that relation, and we already know p is equal to n2 minus n1 by r. So from that we can establish this thing where r is equal to n2 minus n1 by r. So this is with the sign convention, and which is also the law of refraction from the curved surface. So now we know lambda 2 x2 lambda 1 x1 equal to 1 plus pu by n1 minus p01 plus 1 minus vp by n2. So you can say that this is the total matrix for the refraction from for image formation by spherical surface. This is the total matrix, and from that we also get the value of magnification, that is x2 by x1, which is 1 minus vp by n2. If now put the value p is equal to n2 by v minus n1 by u, we will get this is n1 v by n2 u. So the magnification is basically this. Please remember. And this matrix is the matrix for image formation by spherical or surface using refraction. Now we are going to coaxial optical system. So basically coaxial optical surface is like an optical system. Instead of having a single reflecting surface, there is this is a black box kind of thing. In this black box there can be many things, 10 lens, 100 lens and something. So basically whatever the many things that will be given to us. Okay, sorry, the call has dropped. So So again, start sharing. Okay, so inside this black box there can be different kind of thing, different kind of lens, concave, convex, refraction, not reflection or refraction, all those things will happen, and that will be given to us for a different case scenario. But for now, this is the black blocks, and this black box is defined by a matrix A11, A12, A21, A22, and for different case scenario, this A11, A12, A21, A22 will change. So the coaxial optical system is basically there. That is the system of lenses and other different kind of lens system, and that can be anything. So if there is an object O, so that this is the black box. So and the image is formed at I. So this is lambda 1 x1, again the thing lambda 2 x2. So lambda 1 dash x1 dash, this point and this point is lambda 1 dash dash x1 dash dash. So what our main concern is that what will be the matrix. So again, as the last, same as the last thing, we need to multiply here that this is the translation, this is translation. So we will start from the I point. So first this translation, so that is 1 0, and we also assume that this distance is d2. So the distance is from this refracting surface, right refracting surface to the image, and this is in the left refracting surface from the object, that should be minus d1. And this side, this is n2, this is n1, and inside the lens optical system there can be different kind of refractive index also. The radius of curvature for the left refracting surface is r1, and the radius of the curvature for the right refracting surface is r2 basically. So we start from the extreme right hand side. So this is with the translation matrix. So thus plus d2 n2 1, and this side will be minus d1 n1 1, and this is lambda 1 x1, and this lens system is defined by, because we don't know when we will be given that let's say there is a 5 lens, then we will know that the lens system is this, that like what is a11, what is a12, what is a21, what is a22. So this matrix is for the coaxial optic system. So this becomes a11 minus a12 d1 n1. This remains a12. This is a11 d2 n2 minus a12 d1 d2 n1 n2. minus A22 D1 N1 plus A21 minus A22 plus A12 D2 N2, and here it is A22 plus A12 D2 by N2. Okay, then another again for rays imaging from the axial of x1 equal to x2 will be 0. So this whole thing we can set to 0. That's the thing. And we know this x2 by x1 is m. So basically this is m, and like other reflection matrix and translation matrix, this matrix, let's say this is A, the determinant of A is also 1. So basically the x2 by x1 n is equal to A22 plus A12 D2 by N2. So always remember, this is gonna be your magnification. So you just need to figure what is A22, what is A12. And as the determinant of A is equal to 1, so A11 minus A12 D1 N1 into A22 plus A12 D2 N2 is equal to 1. So if this is m, this is 1 by m. So we have reduced the matrix size to lambda 2 x2 is equal to 1 by m A1 to 0 m and lambda 1 x1. So this is very important form. And what is m and what is 1 by m, you need to remember always. 2 into and 1 by m is equal to 1 1 2 minus a. Achha, okay, a11 a11 d1 n1. Always remember that. Then comes another thing, that matrix for thick lens and matrix for thin lens. So for same thing for thick lens. So first, so matrix for thick lens. So for matrix for thick lens, basically we are not now take into account this translation and this translation, because we have already established the matrix for coaxial system, which is this. So in this d1 and n1 will basically take into account this thing, but for matrix of thick lens we only take a refraction matrix for this surface, R2 surface, then the translation here, which is basically t, so 1 0 0, sorry, and this is 1, and this is t by n, whatever will be the refractive index of the lens, and this is the refractive matrix for R1. So that would be basically 1 minus P101, and this is 1 minus P201, and the multiplication of this. So the assumption for thin lens is t is equal to 0. Don't put t is equal to 0 here. Even if you put that will be good, but it's a best practice. You multiply the matrix, then put t is equal to 0. So for thin lens, the matrix is basically lambda 2 x2 is equal to 1 minus p1 minus p2. So 0 1 lambda 1 x1. So from this you get a important. So now if we compare with this matrix to coaxial matrix A11, that would be 1, A22 would be 1, A21 would be 0, A12 would be minus P1 minus P2. So from this we get to know the important equation, which is basically for the lens system, for thin lens 1 by f is basically this is n minus 1 by r1 minus 1 by r2, and n is equal to n2 by n1. That's the relation. And for thick lens 1 by f is basically n minus 1 by r1 minus 1 by r2, and here comes the additional part, n minus 1 whole square t n r1 r2. So always remember that part. So let's a quick recap. We see the translation matrix, we see the refraction matrix, and how we need to multiply and get to the bottom of it, and the actual matrix, which will say the image, and it can be many things. We can multiply for each surface, but that would be a cumbersome process. So that's when we introduce the concept of coaxial matrix system. So make things easier, we have assumed that there is a black box and a translation, then a black box, then the translation again, and in that case what it would be the magnification and what will be the matrix. So that will be the matrix and then magnification. Now our goal is to remain only to know what is A11, what is A12, what is A22, and what is A21. We don't need A21 because A21 is not that important in any equation. A21 only appears in this like element, but this element is it's anyway set to 0. Okay, just this one. now we go into unit plane and nodal plane concept. So what is the unit plane? Let me check. So for unit plane, so the object and image will be the same height for unit planes. Like this is the unit plane. If this is a unit plane and this is a unit plane, so if we put a object here and we will get an image here, they will be of the same height. And for this, assume there is an object plane that is minus d1 direction, this is minus du1, this is minus plus du2, and this is the object plane that is plus d2. So basically magnification is unity. So the professor has described the mathematics very well. So now we need to find the position of du1, which is basically a11 minus 1 n1 a12, and du2, which is basically 1 minus a22 n1 a12. So how this comes, it has been discussed in the class. And now it basically comes from the thing that n is equal to 1, which means a11 minus a12 d1 by n1 is equal to 1. Here d becomes du1, so from that you get that equation. And another thing is, and then the professor has discussed some questions. He has discussed those questions very well. So I think I don't think I know that you have able to understand that. And then there is another plane, that is nodal plane. So between the nodal planes, the angular magnification, relative angular magnification is 1 basically. So again, with all the calculation and all those things, it became that dn1 is a11 minus 1 by a12, and dn2 is basically, so what is again dn1? So this is the nodal plane, so this is dn1 and this is dn2, so this will be minus. Okay, dAu would be 1 minus A22 by A12. So this is basically actually du1 and du2. When media of either side of an optical system have the same refractive index, that will happen. So that's the case. Then there is a like system of two thin lens. So from that you got to know that. Then again there is a matrix multiplication, and from that you got that 1 by if the focal length of system of two thin lenses would be this, and here t is the like distance between f1 and f2 lens that you need to remember, and the unit places will be given by tf by f2 and minus tf1 by tf by f1. So these are basically the different equation we need throughout the question solving. So now get into that. The professor has already discussed 5 or 6 questions in the class, and that should give you the basic idea, and that is basically enough. But I'll discuss some quiz question or assignment question from the week 2 previous year, and then some question from Ajay Ghatak and all. Question from the book written by Professor Ajay Ghatak. So, question 1 from the week 2 previous year, that the matrix for refraction from a convex lens of focal length f is so for refraction we know that is 1 minus p01, and p is basically n2 minus n1 by r. So it becomes n minus 1 by r, 1 minus 1 by r2, like this, and this is basically equal to minus 1 by f. So this is plus 1 by f, so this is minus 1 by f 1. second question is the system matrix of optical system is given by 1.501. The focal length of the optical system will be P1 will be 0.5 unit, 2 would be minus 2 unit, C would be 2 unit, and D none of this. So answer is minus 2 because matrix is 1.501 and 0.5 is minus 1 by f. So basically f is minus 2 unit. So we need to remember these things, that what is what. We know that from the lens equation, that for the system of lens, what is the for the system of lens also we get 1 minus t by f2 minus 1 by f0, 1 minus t by f1. So this is 1 by f, so minus 1 by f is equal to 0.5. The question number 3 is the system matrix is for a convex refractive surface of radius, convex refractive surface of radius of curvature 5 centimeter and refractive index 1.5 is. So instead of giving the different kind of answer, let me give you the direct answer. The system matrix for a convex refractive surface, the radius of curvature is 1 point. Radius of curvature is 5. And the refractive index is 1.5. So the refractive index is 1.5. So basically what will be the answer? So convex refracting surface, so we know that is 1 minus p 01. So p is equal to n2 minus n1 by r. So it would be 1.5 minus 1 by 5. So that would be 0.5 by 5, that is 0.1. So the answer would be 1 minus 0.101. That is the answer. We just need to obtain the p-value. Now question number 4. Excuse me please. The system matrix of optical system is given by A, B, C, D. Then magnitude of optical system would be magnification. Yes. Magnification of optical system is question number A. Option A. Oh. Option A is D. Option B is C. Option C is 1 by B. Option D is B. So we have already know that this thing is magnification, and here that is D, so answer will be D. So then question 5 is basically focal length of the thick lens is given by by the question 1 was 1 by f is equal to n minus 1, 1 by r1 minus 1 by r2 plus t by n r1 r2. b is 1 by f is equal to n minus 1, 1 by r1 minus 1 by r2, n1 minus t by r1 r2, and c is 1 by f is equal to n minus 1, 1 by r1 minus 1 by r2 plus n minus 1 square t by n r1 r2, and t is 1 by f is equal to n minus 1, 1 by r1 minus 1 by r2 plus t by r1 r2. So we know that the correct answer is this, C. And question C is for a sphere of radius 6 centimeter and refractive index 1.5, the focal length is 9 centimeter, B 0.11 centimeter, C 0.167 centimeter, D is 6 centimeter. So we know f is equal to n minus 1, 1 by r1 minus 1 by r2. So this is a sphere. basically for this surface, one and one will be positive and another will be, this is the negative, this is the positive, so that will be 2 by r, 2 by r, so that is 1.5 minus 1 into 2 by r, which is 6. So that would be the answer is 1 by 6, so that would be the answer is 6 centimeter. Equation 7. The system matrix is minus 5, 0.330 b. Then the value of b is a 0.5, b 0.667, c is 0.2, minus 0.2, d is 3. So the value of b, because the determinant of this will be 1. So minus 5b equal to 1, so b equal to minus 1 by 5. So that will be minus 0.2. So that is the answer. The question 8 is the system matrix for a lens combination of two convex lens of focal length. Lens 10 centimeter and 5 centimeter separated by a distance 15 centimeter is. So we know the equation would be, the system matrix would be 1 minus t by f2, then minus 1 by f1 plus 1 by f2 minus t by f1 f2 t 1 minus t by f1. So we know t is 15, f1 is 10 centimeter and f2 is 5. So 1 minus 15 by 10 would be 1. First t by f2, that is 15 minus 5, so 1 minus 3, so that will be minus 2. So this will be minus 2, this is 15, 1 minus 15 by 5, this is 1 minus t by f2. which is 1 minus 15 by 10. This is 1 minus 1.5, that will be minus 0.5. So this is minus 0.5. Now we need to calculate the focal length, that is 1 plus 1 by f2 minus t by 1 f2, that is 1 by 10 plus 1 by 5 minus 15 by 10 into 5, 10. So this is 3 by 10 minus 3 by 10, this is 0. So the system matrix will be minus 2, 15, 0, minus 0.5. This is the answer. And question 9 is the focal length of a combination of two lenses of focal length 15 centimeter and 10 centimeter separated by distance 5 centimeter is. So that is 1 is equal to 1 by f1 plus 1 by f2 minus t f1 f2, that 1 by 10 plus 1 by 15 minus 5, 10 into 15, 3. So that should be 30. So 3, 2 minus 1. So that should be 4 by 30. So f is equal to 30 by 4 or 15 by 2, that is 7.5 centimeter. So answer would be, that is in C option, 7.5 centimeter. Question 10. The correct statement for the unit planes are, so there are many statements that the planes in the object and image space between which focal length is identical, so that is not unit place. Planes in the object and image space between which angular magnification is unity, that is nodal plane. And plane in the object and image space between the magnification is unity, that is the unit plane. So that is the answer. The magnification is unity. That is for today. I may discuss some of this matrix question, one or two different kind of question in the next class, but whatever the professor has described and whatever I have discussed from the previous year week 2 assignment, I think that should you will be able to finish assignment 2 by tomorrow. Thank you.